Hi, everyone. Welcome to our webinar, jointly prepared by Altera and CodiLime. Today's session is Hardware Accelerated Security, powered by AI and P4. And this is the result of our collaborative efforts. My name is Tomasz Janaszka, and I am a solution architect at CodiLime. Working in R&D section, I specialize in identifying and exploring insightful AI/ML techniques that could be used for solving real problems within, but not only in the networking domain.
Good morning, good evening, everyone. I am the principal engineer at Altera. My name is Mirek Walukiewicz. I'm working mostly with the networking technology and providing the acceleration solution for the FPGA using customers of Altera.
Okay, let's look at the agenda of today's meeting. We will start with the introduction, just to provide the context of our topic and to answer why we are dealing with it. It will be followed by the live demonstration, showcasing the SYN-Flood attack detection in action. After that, we will switch to the section with solution overview, explaining some details how we prepared this demonstration. Next, Mirek will explain other use cases that could be created using a similar approach to this demo. We will also review the benefits we could achieve using our approaches. And we will conclude with some takeaways, opening the Q&A session. So you will be able and kindly asked to ask questions about this topic in the Q&A panel. So growing demands for ever higher data transfer and data processing speeds in networking infrastructure forces us to look at the solution that could be accelerated by hardware. So here are, you can see requirements that modern network security solution should meet in order to remain effective in today's dynamic and continuously complex environments. So flexibility is essential because such a solution should support diverse protocols and traffic patterns in various network architectures. Also, such a solution should adapt quickly for evolving threat landscape and changing user behavior in order to ensure protection against emerging risks. High accuracy in detecting threats is paramount, similarly as ability to ensure low latency and high throughput in real-time processing in high-speed networks. And finally, efficient resource utilization is essential to provide high performance at reasonable costs. So we believe that the combination, the mix of technologies like FPGA, P4, and AI/ML is designed to fulfill those requirements, and Mirek will elaborate on it.
Yeah, but why FPGA and P4 and AI/ML? Today's the problem with the security and the processing, the networking traffic with the AML is just the speed of the traffic and the different KPIs like the packet processing speed. And today's well-known AI ML systems like the base on the GPUs, on the CPUs, are very slow for that kind of the processing. They can achieve the 100, maybe 1,000 inferences per second, including the standard way how they get the feature to be trained and processed by the AI ML inference. Yes, using the hardware and the FPGA or it makes possible that we can use the same approach like in large network, but we can achieve the much higher speeds. Yes.
Okay, so maybe we could now switch to the live demonstration that we prepared, having in mind the requirements and this mix of technologies that we used to create it. We will be demonstrating the detection of SYN-Flood attack. But before, let's explain shortly what the SYN-Flood attack is. So this is the special kind of denial of service attack when the attacker sends a huge amount of TCP SYN packets in order to initiate connection to the attacked server, but deliberately avoiding completing the handshake. As the results, the server stuck to allocate the resources, eventually overwhelming the system. So the result is that for the legitimate users with the new session, the server becomes unable to handle them efficiently. So definitely, we would like to detect such attacks as fast as possible. In our demonstration, we combined P4 and AI to detect patterns in the stream of the packets at the input. And the role of P4 is to filter those packets and to count them. In that way, to evaluate the SYN packet ratio in a very short sampling period. And next, this feature is used by AIMM model, which is embedded in FPGA to decide whether the attack is present or not. And trying different models, we obtain from 4 to 11 million inferences per second, so it is very fast. We use this simplistic scenario because it is easy to visualize during this webinar. At the same time, it reflects the real-world use case and allows us to show the workload and to show the potential of this solution. It's worth to note that similar approach can be used to solve many problems when the quick detection of anomaly in network traffic is required.
Let me explain a bit how the demo looks like. Yes, we will see during the live demo. We have the server, which has the two cards. One card is working as the traffic generator, and the second card is the FPGA, where we incorporated the P4 extractor, P4 SYN-Flood rate extractor, and inference engine, AI ML inference engine generated from the Altera tools. And as the effect, the inference engine just sends back the packet to the application, so we seeing the result of the inference as the application showing that two windows, so the two colors of the windows. Yes, when we send it, when we see there is normal traffic, the window will be green, and when the SYN-Flood is detected, you will see the red window. Yes, let's go to the live demo presentation, and let me share my screen. Yeah, that you can see the application is here on the right side, and you can see the server. To sending the traffic, we are using well-known TCP dump traffic generation. We are using exactly the same packets which were used for the training of the network. Yes, and here let me just send the start the traffic generation. Currently, the state is that we have the normal traffic. You can see that currently I have the special pickups created when we sending some number of the SYN packets inside. And okay, and that finally it is detected, yes, here. And next, we can send the normal traffic. And you can see that the color change. It means that the SYN-Flood detector detected saw that the packet rate of the SYN-Flood rate or the SYN rate detected was the small enough to make sure that the probability of the SYN-Flood detected is the really enough. Yes, the simple demo just shows how the FPGA system could be incorporated with the firewall or the firewall application or any kind of the application running on the server.
Okay, so let's switch back to the presentation.
Tomek, let's explain what we really did in this demo. Yes, what happens inside of the system. Yes.
Yeah, so now we read the solution overview, because let's perhaps first start to explain where the key logic of our demo resides in the hardware.
First of all, let's start from the tools what we are using. The Altera, together with partners, yes, preparing of the FPGA card, yes, because our mission of the Altera is to enabling of the using the FPGA to the even people which are not able to program FPGAs. And it is reason the one problem what the customer normally has is how to use the FPGA. So we have the cards, yes, here like this SmartNIC card, and the second part is how to program FPGA. Programming FPGA is the complex enough, considered to be complex. So for the user who wants to use the FPGA, we're creating the special design for the AI ML. Of course, the FPGA could be used for 1,000 any reasons, but we are talking today about the machine learning, and we're creating the model where we can put to the FPGA the code written in the P4 and code which is trained result of the training from the tools like the TensorFlow. And as we will explain, and the result of this one is the put inside of the FPGA as the two blocks. Yes, the first block is the making the packet preprocessing and the feature extraction, and the second block is the making just the determining the making the decision. Yes.
Okay, so now we know where the key logic resides in the hardware. Now let's say a few words how we prepared the model. So first of all, we prepared traffic scenarios, various traffic scenarios, and some of them were designed in the way to overload the server. And the other represented the normal traffic, which the server was able to handle without any issues. And we used that scenarios in our traffic generator, and we recorded the pickup files for further processing. But one important point here is that we grouped those pickups into say groups, one representing the situation with the SYN-Flood attack and another the normal traffic. And having that, we created the code for the extraction of the features that are relevant and helpful in detecting this particular kind of attack. As we previously grouped these pickups into those indicating SYN-Flood and representing normal traffic, we are able to create the table of features with corresponding labels. And this is the foundation for training and testing our detection model. However, here we would like to stress that there is a need for close collaboration between data scientists or ML engineer who is preparing data for building the model, and with the P4 engineer, because the goal is here just to assure that the feature extraction is the same in both words. So during the preparation of data for training, and the code should be similar in P4 because at the end, this will be the deployed code, and the same kind of feature extraction should be in both words. And this is very important, especially the same sampling period have to be used in both cases. But having that, we having this feature table with corresponding labels, we need to create machine learning model. In our case, this is the binary classifier outputting whether the SYN-Flood attack is present or not. To do so, first we need to select a machine learning framework like scikit-learn or XGBoost or TensorFlow, and to select appropriate model type, because this classifier can be built using a simple decision tree or random forest classifier, or we can build classifier based on neural network applying deep learning approach. So if we select the model, then we need to train it, to evaluate it on the data that were not used during the training. And each model usually has some bunch of the hyperparameters that we need to set in order to optimize the final performance of our model. This process is iterative. It means that if we at the end cannot reach required accuracy in detection, then we need to go back to select another model, or even get back to the previous step to extract additional features for creation the model. And the last step is to transfer this model into the FPGA hardware.
Yeah, thank you, Tomek. But for the more advanced AI user, let me explain that we're trying to solve the SYN-Flood protection problem as the measuring of the probabilistic density in the multi-dimensional feature space. Yes, so
yeah, in 6 dimensions.
Yeah, exactly. When the only single dimension is used. Yes, but going back to the simple topics. Yes, here as I say, the Altera is preparing the tools to making sure that this transformation could be made in easy way. Yes, our job, our work here is to simplify the process as much as possible. When we are using the ML classifier, we're creating the ML classifier in the toolset. Yes, in the TensorFlow here, for example, we generating the ML classifier. We can use, for example, the tools like the Altera FPGA AI suite to create the code which is the readable to be used by the other RTL specific tools, which could be transformed to the something which is understandable by the tools, that could be used by the tools which are really the preparing of the bit stream or the final binary final file to program the FPGAs, yes, which is the set of the bits representing the weights, representing the transformation, the levels, the function, the decision function here. And here to the transforming of this one, we have the scripts, we're delivering the scripts that the customers or the users of our tools just using the standard Altera Quartus tool can generate such big stream. Yes. At the end, it is very important that making sure that during the simulation that we achieving with the RTL code, with the FPGA code, we achieving the same probabilities and the same result like it was the available or the trained when we are using the TensorFlow.
Okay, so I think it was the major steps for the preparation of the demo of this kind, as we showed. So now let's switch to other use cases that could be developed using similar approach and similar mix of technologies. This will be predictive failure analysis, volumetric data preprocessing in large networks, and AI-based congestion control for stateful protocols.
Let me explain the few use cases. Yes, Atomic say the first of all, the very typical use case when almost everyone can think is the anomaly detection here, which is the typical work made by the AI today. Which in the today's systems, when we have the FPGAs, when we have the which normally are located on the board, the FPGA is able to getting the information about the sensors and getting generally the state of the ASICs on the board or the whatever it is, the server, switch, router, everything. And here the IA engine, if this is trained correctly, can detect the filers, anomalies, yes, here, and detecting of the some difference, yes, which are the could be the very difficult to find by the users, very difficult to find by the users of the operators, yes, without this one, yes.
Okay, so you are saying that we could know that this particular device is going to fail in the near future. So we could know it far enough because the total collapse, and then we could better plan necessary repairs in our network before they became detrimental to our network.
Yes, exactly. That's the reason for this one is funding them in this different ways, the very complex process really.
Okay.
Yes, so. And the same problem, what is in very large networks, yes, here, because the problems happens when we are going into the high scale, yes, here, in large network, today, the people are asking not only get me the highest possible throughput, yes, the problem is different today. The problem is to get me throughput what I paid, yes, here, because it is the question of the hardware monetization of the network infrastructure monetization, yes, here. And normally this process is solved today by the adding of the telemetry. But if the network is going large, very in the large scale, the number of the data, telemetry data, which is required to be analyzed, the system is going so high that the simple analytics system is simply overloaded. Yes. So our solution for this problem is if we have every component of the network, yes, of the infrastructure, can measure some kind of the dynamics of the system or some KPIs of the network KPIs that it is, for example, like the latency, yes, which is required for the specific use case, yes, that it is possible, for example, to make the pre-processing per device and sending the information about on my point, for example, the anomaly detection or some difference happens or not here. It just makes sure that the analytics system could be usable here and not completely overloaded by the size of the amount of the analytics data. Yes.
So moving this computation of the necessary traffic statistics closer in these devices, so we can achieve quicker and better statistics about the traffic.
Yeah, not only the traffic, statistics about the traffic, we can detect for example, something wrong happens. Yes, here it is not only statistics. Yes, it is much more than it is. We can achieve much more.
Yeah, but the scalability here is the issue, the major issue.
Yes, exactly. It is. We are doing everything for the scalability.
Okay, so let's move to the last use case.
Yeah, the last use case is could be I call this the AI-based congestion control for AI NICs to implement complex AI networks. The AI network is, for example, used during when we need to implement huge transfer related to the LLMs, yes, training process, yes. The LLMs implementing of the infrastructure to the training of the LLMs requires the incredible speeds and the incredible latency in the system, yes. And the servers of the devices, yes, making this processing communicate with each other using some models, some operation which calls the collectives. And there are some collectives which require sending the data from the multiple server to the single one, yes. Even when this saving server can receive the 400G, it is incredible speed when, for example, 400G servers is the pushing traffic to them. It's not able to solve. So normally we're solving these problems in the traditional networking by the implementing of the congestion control. Here, the problem with the AI NICs is the problem that we should go into the AI. We need to implement congestion control completely in the hardware, yes? And here there is the hundreds of the congestion control algorithms. And with this congestion control, the congestion control algorithm is the heuristic, yes? You get some data in, you get some data out, and every congestion control works differently. So we believe that we can train the model, yes, which can implement, we can have the one single implementation of the congestion control module and provide the different models representing different congestion control algorithms, yes, so we can control the traffic flow in the network, yes, here.
So just to summarize, when we need to serve smoothly this type of huge data transfer from end devices to one devices at the same time, so which is typical for LLM training process. So this kind of implementation can just allow us to adjust this congestion control mechanism, particularly for this type of data transfer.
Yeah, exactly.
Okay. Okay, so thank you for this explanation. So let's review the benefits that we could achieve from presented approaches. For sure, that enhanced network security, supported by AI. Sorry for that. Allows us to reduce the downtime of our infrastructure, and in that way preventing financial or reputation losses. So applying predictive maintenance, as we described, we can improve the network reliability, but we could also expect some cost reduction because replacement of the failed devices far before they completely collapse is much cheaper than performing the same in the emergency situation. You mentioned a couple of use cases that really could improve the performance and efficiency of our network. So we could expect better utilization of bandwidth and less congestion in our network, all contributing to a superior user experience. So real-time responses, quick responses in identification of anomalies and threats means that we could make faster decision about the mitigation actions. And we also showed that this FPGA is really scalable and is flexible because we should have in mind that we could reprogram this infrastructure if the conditions change significantly. Or, for instance, we need to cover another type of attacks.
Yeah, exactly. Very good summary.
Okay, so let's provide some takeaways from today's webinar. So traffic detection, malicious traffic detection, supported by hardware, accelerated by hardware, and supported by AI models, offers us the solution which is both efficient and accurate. However, to do so, we need to prepare the models in the proper way to optimize them and to prepare them for the FPGA deployment. So it is not easy task. However, in Altera,
yeah, in Altera, we are working to provide, to making FPGA programming as easy as possible, yes? So for this reason, we're providing the tools like the Altera P4 suite for the FPGA and Altera FPGA AI suite with the support, so that even engineers without extensive FPGA expertise can build the high-speed AI ML applications, yes?
Okay, so we have the tools, but it is good point also to ask the expert about some details. Nevertheless, okay. Okay, so we covered all the materials that we would like to present today. So now is the time for your questions. And let's see, we will be reading them if they are not too long.
Okay, the question is to I'm curious to know where exactly the IAML algorithm is running, host or between core of the FPGA. Let me explain this one. Definitely above in the system, above the future extractor and the IAML model is the part of the FPGA that it is. And second question, what is the communication path between the algorithm and the SmartNIC? Because in the model here, what we have, the P4 is making really the two functions, yes. One function is making the pre-processing of the data and moving this one or the changing this data or the generating the futures for the AI ML engine as it's making future extractor, and also it making the post-processing, which is also the result from the AI ML engine, which is really what we call the AI ML engine from if you are the P4 expert, maybe you heard about the extern, yes? We are keeping the P4 AI ML engine like the P4 extern, yes? This P4 extern just generate the response, and we encapsulate this response into the packet and sending the packet to any direction. In our case, it is sent to the host over the DMA over the card. When the result of this one, you see this changing window, this green or the red is just the effect of the post-processing made by the P4 and P4 code generated, packet generated by the P4 code making the post-processing of the result, yes.
Okay, so next question.
Second question, what is the throughput of the system? Generally, the throughput of the system depends on the model, what you are using. And currently, the bottleneck point is really in our test, what we made, the bottleneck is related to the speed of the system of the model, yes? We are using simple model.
So the inference time of the
inference,
model, yeah.
yes, here. And depending on the model, we achieve for one model, we achieved, for example, the 4 million inferences per second. For other models, simpler one or the generating different, we achieving the 11 million inferences per second, yes. So, but it very much depends on for example, complexity of the model, yes. And really the big problem here is to finding a balance, yes, here in the different directions, yes, balance between the size of the feature extractor and balance on in the inference engine. Yes, if the inference engine is too complex, yes, it will be smaller. Yes, it will consume a lot of the resources. Yes, in the FPGA. So it always we should always making such design. We always should balance between the size of the feature extractor and the decision making. Yes, here.
Yeah, and different models contains different number of the parameters, and that influences the time of the inference.
Yeah.
Next question.
Yeah. Next question is can you point to any model can predict the failures based on data from sensor?
So we didn't consider in our say preparation for these models for that. So we just mentioned that this is the huge number of information, and we should apply a kind of model for detecting the anomalies in here. But one single anomaly probably is not enough. So we should design a kind of meta model that is collecting the number of say anomalies in the unit of time, and perhaps that way to design the model that is able to answer whether this behavior of particular device is expected to be failed in the near future. So, but definitely the anomaly detection, one of the anomaly detection model need to be used here.
Yeah, but here is the important thing to think about the first of all, you should grab this feature, this sensors is here, and next to some way you should connect them to the or making some transformation of the values, yes, of the sensors, yes, whatever they are, into the features, yes. Here, the people today, when people are talking about the ML engines, yes, they are mostly, when we are talking about the LLMs, really the feature extraction is the process which is very well defined. Yes, here you know, for example, you have here is the bit mask. Yes, here and the problem what the people trying to solve is the inference engine. Yes, in our case, the problem was how we can transform the features from the packet, from the sensors, to making sure that they are transformed and they could be used and be understandable by the model of the model created on the FPGA. Yes, how we transfer this feature, this sensor, yes, into some features which could be trained. Yes, here. The next question, what we see here is what is the size resource utilization of the ML engine? As I said, our model, what we are using, for example, we're using the model with the Keras, yes, here generated by the Keras. It was about I believe, as I remember correctly, but it is very low number. It is the 10% of the Stratix 10 FPGA. Yes, if you can explain what this model is doing, yes, and how is the size of this model, yes, because it is very, very important, yes, because it is not definitely LLM, yes.
Yeah, it is not LLM because the purpose of this model is just to detect simple detection whether we have the pattern that indicates that it's a SYN-Flood or not. So we use many models, but the biggest one consists of 3 layers of neural networks, outputting the binary value between 0 and 1, meaning that 1 is flood attack or not. In total, it was quite small. It was 10 of mega maximum, so it's quite small model. But the issue here in the demonstration was to show how quickly we can get the response. So that was our major purpose. However, the similar approach could be used to much bigger models, but then the steps from converting this model into the FPGA is much more complex, because then we need to use some optimization, quantization of weights. So this is always the balance between how much the model will take in the memory and how accurate it will be and how fast will be the inference. So this is the trade-off between using some parameters, we could just achieve different results. Okay, so we finished the questions. Thank you very much for them. Thank you very much for your attention.
Thank you very much for your attention.